Okay, everyone, final review session. This will be about 2 hours, and let's see, you know that the last class, I know, went a little bit long. That was a little bit of a review on Boltzmann Equation, so I won't spend too much time on that. And I'm also mostly I'm not gonna really say too much about everything from exam 3. And again, you just had that exam, right? So you should be well studied for that. It would not be sensible for me to spend time on that when I can spend time on other things. I can easily go through 2 hours of stuff without approaching exam 3, which is going to be way better for you. The exam right now, I haven't quite finished it yet because again, it's been really hectic around here, I'm sure for you as well. Right now, it's definitely far more on the descriptive side because, you know, what else could I possibly have done? So just note that. So it's more like explain why quantum mechanics is quantum mechanics. Okay, that's stupid. But anyway, there's more questions like that. The derivation questions still have derivations, but they're simplified. To be honest, the last test, those derivations were pretty simple too, right? So they're about on that same level. And of course, it's comprehensive. And I do have one question right now, maybe two, at least one, on the enzyme kinetics lecture, right? Because after exam 3, why have classes if it's not anywhere, right? So one, possibly two questions on enzyme kinetics. Note that was not terribly difficult, right? Let's see, okay, some weirdness. I hope this looks okay because I'm in a different room because I went to the normal room and there's a bunch of guys playing Dungeons and Dragons, and so it was such a freakish thing. I didn't want to like move them. I just kind of backed slowly out the door. So I'm in a different classroom. But I'm looking at the video monitor. It looks like it's coming out okay. So, all right. With that, again, let's start with. I'm mostly just going to cover test 1 and test 2, which of course we started out with Maxwell Boltzmann. And the way I tend to do this class is the terminology can get confusing, right? Because what I always, I do a lot with the Boltzmann equation, right? Boltzmann equation is a probability density. Remember, that's different than a probability because probability densities have units, right? It's the inverse of whatever they're the thing of. So they have to be integrated or summed. You have to do something with them in order for them to equal probability, which again, probability is that thing you knew since kindergarten. So the Boltzmann equation for probability, for the probability density of something having a certain energy is something that can be derived, and I told you I wasn't going to do it. It involves some specialized mathematics. And it's, that bothers me, there we go, KB, that's better. It involves some specialized mathematics that, and it takes a long time. It takes about a full lecture. So here we go. So remember, this is actually just the Boltzmann equation. And now that you've had a decent amount of quantum mechanics, hopefully the normalizer is more sensible to you. And again, this last lecture, last Wednesday, or today's Wednesday, I'm confused. I did a bunch of things with this, so I'm not going to say too much about this. Again, this is the Boltzmann distribution. And now that you've had quantum, hopefully the sum of energy levels is like a lot more sensible to you. Actually, I really struggle. Remember that the Maxwell part of Maxwell-Boltzmann is when you plug in velocity. And I had a hard time like explaining what to do with this normalizer. And hopefully at this point you're like, oh yeah, whatever, that's not, it's not particularly difficult at all, is it? Well, that's because you've seen it a zillion times. Let's see, now again, before I get to Maxwell-Boltzmann, let me just focus on Boltzmann. And what do probability distributions, probability density, the same word, different words for the same thing. You can calculate averages, which would either be the sum of all states of the energy times the probability of observing that energy. So I'll put a little I there. That you don't really need that. Okay, so this would be if the energies are discrete, which quantum mechanics tells us that's usually the case. If energies are continuous, then of course it just turns into an integral. The sum turns into an integral. And partial would be, well, that bothers me a bit. It needs to look better. Oh, this board is awful. I actually wish I was back in the other room. There you go. And remember, I had a lot of questions on this. When do you use sum? And so that was for like COVID patients, because you only have 0, 1, 2, or 3 COVID patients. It was also in the Planck distribution, because we related energy to the number of photons. You can only have 0, 1, 2, 3, 4, 5 number of photons. It helped that we had identities for the summations. You saw some of that last lecture. Now when it comes to things like velocity, right, that's when we get Maxwell into the Maxwell-Boltzmann, then we think, technically the velocities are quantized, and I said that to you even back at the beginning of class, but the steps in velocities are so small that they might as well be continuous. So that's why this sum turned into an integral. Recall that the way, this is how nature partitions energy, the probability distribution of energy, but the way that we put the Maxwell and Boltzmann was, if you have a function for some other property like velocity equal to energy, then you just plug that into all of your energies and calculate the average of again, insert this into the energies, solve the normalizer, do some algebra, you've done it. Once you've done that, you can then calculate the average of that other thing. So, of course, again, the Maxwell and Maxwell-Boltzmann came about by inserting, for wherever we saw energy, we inserted 1/2 mv squared. And now we had a distribution not of energy, but of velocity. But it was still energy, but it's velocity, right? And I thought that was kind of interesting how it's two things at once, right? So what happens is, therefore, and again, I'm not going to do all the steps because that would take way too long. The probability distribution of velocity was, we had the normalizer, which in one dimension, this turns into an integral for Vx, Vy, and Vz, so that's 3 dimensions. Each individual integral is, what was it? It was 2 pi kBt over m. But to the 1/2, but of course it's on the normalizer, so I flipped it 1/2 for 1 dimension, but we live in 3 dimensions, so this ends up being 3/2. So again, as I've stated, especially ad nauseum last lecture, you got to figure out the normalizer, and it's got to be a bunch of constants, because otherwise, with this, if it's still this kind of sum, it's like, well, I don't really know what that is yet. Okay, so that's the normalizer. Here is the part of the Boltzmann distribution that is there no matter what. Remember that I like KBs as opposed to Rs. R for the gas constant 8.314, because KB, the gas constant over Avogadro's number, it's the gas constant for a single molecule. And I've always tried to emphasize for this class, to be like, okay, here's what a single molecule does, here's what a single molecule looks like, which is one of the reasons I wanted to do the last lecture and show how Boltzmann can connect the single molecule quantum to macroscopic thermodynamics. So normalizer, that part from the Boltzmann equation, and then we had these partials. Recall that these things, we spent quite a bit of time on this. I've spent quite a bit of time on Jacobians. Now, unfortunately, I've not finished writing the exam yet. I am thinking about trying to write a Jacobian question, a what's wrong, or a short answer. I don't think I'm going to put one in the derivation section, but God knows I spent a lot of time on Jacobians. I'm almost out of room. I mean, the test is almost done, but I would like to put a Jacobian in there. Now again, you may recall some of the fancy graphics. I spent quite a bit of time on those to show you how these partials in x, y, and z, to turn them into a net partial, you get a 4 pi v velocity squared. And remember that the way to think of partial x, partial y, partial z is like the volume of a cube. And when we integrate this, because when we have partials you have to integrate, that volume is growing. So as the cube gets bigger and bigger, it looks more like a sphere. And how does the volume of a sphere grow? Well, it grows as its surface area times its thickness. So again, you've seen that. I know that it's kind of hard to really express that. That's the best I can do. Now you can also just use straight up the formula for Jacobian to do that as well. Now also, one thing is, because you have partials, as I mentioned, you have to integrate this thing. And let me write that out. Okay, let me go up here. So of course, if you integrate a Maxwell-Boltzmann distribution of velocity, which of course looks like this. Of course, limits, you have to be sensible about limits. On questions, I've always given you, because I have to, either told you what the limits are or made it like stunningly clear. And, I try to make it, sensible even without me telling you, like number of cats, you can't have a negative cat. All right, but if you're talking about like velocity, net velocity, you can't have a negative net velocity. But Vx, Vy, Vz, those could be negative because things can move backward. So again, I know that's a lot to throw at you, but it's really sensible. So I'm sure I'm going to have a question like this, and I will make sure that the limits are clear. So there is our Jacobian. Here's our normalizer again, flipped over from the 2 pi. God, this board does not erase well. E to the minus. I don't know why I'm writing this down again. It's kind of stupid. Okay, so of course if I integrate it, you should know that you're going to get 1, which is the last point I want to make about probability distributions, is they have to integrate to 1 because you have to have a finite probability of something happening. So in this case, if I want to explain an equation to some high school student who hadn't had calculus yet, what this means is that there's the probability that a molecule either has velocity or does not have velocity. It's either moving or not moving, and that's 100% certain, right? Cool, I mean, it's cool, that makes sense, it's cool that it works. How can it not happen, right? It either does or doesn't. Well, yeah. Okay, so note that if you are going to do average velocity, okay, so we're here. So you have velocity times the Maxwell-Boltzmann. So that ends up being simple. Just cube that, and there it equals to whatever it equals. I think I remember, but I won't write it down. So there you go. Remember, you could ask the average of the square velocity. We talked about why why this is true, why the average of the square is greater than the average squared. That is just, numbers just do that. There's actually a bit more meaning to it. When I cover grad school, I explained that the reason that this is true is because heat capacity is positive. It's just a grad school thing. Anyway, let's look at the graph. Some of the things that you can take away from this is you're used to bell curves, right? So, and a lot of processes are bell curve processes, and that's fine. And you see a bell curve right here, except then you get this skew from the Jacobian, the 4 pi v squared. So this is a bell curve, but that's not what Maxwell-Boltzmann does. Maxwell-Boltzmann spills over to the right quite a bit, and that does things, right? So one of the reasons to cover this stuff is that when you run into probability distributions that have a little weirdness, a little skew, things change, right? One thing that changes now, we know the top of the graph is the most probable. That's just where the derivative is equal to 0. It's just the freshman calc definition of the maximum of a function. So whatever, right? But where it gets interesting and counterintuitive, something that Joe Schmo down the street does not know is that the average, the actual average, is going to be canted slightly to the right. Now, this is really exaggerated, by the way. The way I've drawn this is exaggerated. And in that, that weird chapter of that textbook that's, you know, always somewhat being worked on of mine is, it shows you what the real locations are. And it's, again, this is a little exaggerated, but it gets the point across. And again, this is the RMS, right? The root mean square is even a little further to the right. So it just goes to show you, remember, one of the things I was saying about this is that your notions of probability are, well, I'll take 5 numbers and add them and divide by 5. That may or may not be okay, right? It would depend on the underlying probability distribution. Although that's okay with like bell curves, it's okay with top hats. Remember, top hats are for dice, right? You have equal probability of running a 1 and of rolling a 1 or a 6. And so that's like 99% of things. That's why that works, but you do run into this. And that's one of the reasons that we want to cover this stuff in this class is because of that. Recall that also we were able to do some other funky things. We could calculate the average in a particular direction. Actually, I know that one offhand. That would be 0 because you're just as likely to go forward and backward. So that's something you could calculate that would be pretty simple and obvious. We had things like relative velocity, where we are no longer looking into that gas chamber. We're now on top, we're now a molecule, and we have a stopwatch, so we're able to time and measure the speed of other molecules. And the damnedest thing is they're moving, I think they were moving faster, right? So the relative velocity is actually greater than the average velocity. And that's really weird. I've never, to this day, I just don't understand that. I mean, I was able to derive it, so I understand it to that degree, but why it would make sense, it doesn't. I've never gotten over that, and I shouldn't admit that, but it's true. Let's see, yeah, that was really about all there was. And you know, one of the things I did for or to you, I don't know which is the better word, is, you know, one reason I'm always doing average cats in a house or a fish in a barrel is because I don't know how much you really need to know about velocities of gases, but I think it is very good for you to have some underlying intuitive sense about how probability actually works, about what constitutes a real average, because it may or may not be what your kind of middle school intuition says it is, and that might be valuable to you. So, and I know most of you are thinking, you know, I will never use this formula. I would say you're probably 99% likely that's likely true. However, the whole point of all this is, you know, most of your education you probably are never actually going to use. So why do any of it? Well, if you never had any education, I mean, how stupid would you be? I mean, you'd be useless. So you do use this stuff. It's just in a kind of a subconscious way. It molds you as a person, and that's really unmeasurable. But it is happening, again, because the converse is, your whole life, you know, okay, so many of you want to be doctors, so you were only trained on one thing, some biology and anatomy. That's all you ever learned. You would probably be an awfully screwed up, useless person. I mean, you couldn't do your taxes, right? I mean, a lot of the functions that a person needs to be able to do, you wouldn't be able to. So I hope this stuff does something for you. I'm sure it does. Neither of us will ever know what it is. Okay. Anyway, I'm babbling now. So the next subject, of course, was blackbody radiation. And let me write that down. Oh, God, this is dirty. Maybe I need to clean it. Okay, blackbody radiation, and hopefully you're looking back on that and saying, oh, yeah, I remember that, because if you don't remember that, that's scary. And this was about light bulbs. And really what I was trying to do, we spent a week on this, what I was really trying to do, it's a warm-up to quantum, right? Remember the lights in the light bulb? They're all sine waves, right? Up until really the last 3 weeks, everything was a freaking sine wave, wasn't it? So this was your first introduction. And I also like doing this because, you know, you hopefully understand the light bulb, right? So some of the quantum mechanics of rotation in a hydrogen atom is not something I want to begin on day one, but beginning on near day one with the light bulb was probably a good idea. And you also got a look at a differential equation, and this should look pretty familiar. You know, it's the Schrodinger equation if I just had a minus h bar squared over 2m, but the Maxwell equations for electromagnetic radiation are actually a little bit easier. Of course, it's in 3 dimensions. Remember, I began the description of a light bulb with this. And this is Maxwell's, a derivation of Maxwell's equations. And it just tells you what the light in the light bulb, the light in the light bulb, the electric field of the light in the light bulb. Remember that Maxwell's equations are for E and M fields. Light is literally an E and M field. It has to conform to this equation. Of course, what is it? It, as usual, is the solution. Now, this is not energy. Again, we run into this a bunch of times. We have not enough letters in the regular or Greek alphabet for everything. So we have E for an electric field. So this is a description. This is a model for light. Again, a model for light as a cosine or a sine. Again, I bet you're like, oh, well, of course it is. It's a wave. So that's one of the reasons I started out with this, because I didn't want to tell you an electron was a sine or a cosine. But saying that something that you've heard called a wave your whole life, calling that a sine or a cosine is probably quite sensible. Okay, so this is the solution to that. So that has to go into the Maxwell's equation. And we saw it's basically sine x, sine y, sine z, sine t. That's what it came out to. I won't write it all down. I'm not going to ask you to write that down in the exam because that would be crazy. If you did, I would, you probably cheated. So that's what I'm not doing that. But anyway, so let's go to one dimension. Of course, we have a light bulb. We have a light bulb that is L big. So this is L, and so it is a light bulb. There we go. So it looks a little bit more like a light bulb. And what happens is, of course, the longest wave would be. I still don't quite understand this, but this is actually half a wave, right? So that wavelength is 2L, and for some reason that's okay. I never quite got that, right? It seems like a wavelength of L would be the first one. The longest wavelength that would be in the light bulb would be L, not 2L. I don't get that. And then of course the next one is this. And again, you see why I did this, because now it's just like particle and Bach, right? It's really identical. And this is basically sine pi n x over L x, right? And then you have y and z and t and all that. So again, you've seen that. And what do you do with this? Like quantum, and like the last lecture, now that you have a solution to the Diffie cube, to the differential equation, you can now plug that sucker back in and get more things out of it. Now, what we got out of that was technically a degeneracy. I didn't use that term at the time, but what's happening is that as the wavelengths, remember the wavelengths can only get shorter, and that means that they have higher energy. When you get to shorter and shorter wavelengths, it turns out that there's more than one way for that wavelength to fit inside the box. Remember those mode numbers, right? That's n sub x is the mode number. Now, I'm not going to repeat it here because it was kind of long, and really one of the more complicated conceptually things is that mode numbers add up. If the mode numbers add up to the same number, then they have the same wavelength. And there's multiple ways to add. It is like nx squared plus ny squared plus nz squared. There's multiple combinations that equal the same thing, and that's a degeneracy. So what you get out of the electric field equation and the Maxwell equation is you get the degeneracy factor for how many waves of a certain wavelength fit inside this light bulb. And as the waves get shorter and shorter, it actually gets really big, like 10 to the 20. The numbers are really gigantic. Now, the reason that mattered is, what the point of the Planck thing was that we wanted to calculate the average energy. So now E is energy now. God, you know, I wish there was a way to not do that, but I can't, right? Anyway, so recall that we calculated the average energy divided by the volume of the light bulb. That was done because, you know, when they figured all this stuff out, it's like 1900 or something, you wanted, you know, you didn't want someone who built a bigger light bulb to get a completely different result and say, what the heck, right? So if you divide it by the volume of the light bulb, then whatever I built, I should still be able to use these equations compared to what you built. And anyway, so hopefully that made sense. And so what was this? Well, it's still 1 over the volume, but we sum the Boltzmann equation as a function of energy. We multiplied it by energy, and then we had this degeneracy factor. And again, that came about from the Diffie-Q, from plugging the solution, the wave solution, into the Diffie-Q. And it was a clever thing that came out of it. Okay, last bit here was to note that we did this as a function of wavelength, right? So energy, one thing we know about light is that the energy as a function of wavelength is hc over lambda. And so just like Maxwell-Boltzmann, we turned an equation for energy into an equation of wavelength. Now the reason we did that, by the way, is because that degeneracy that we got out of this Diffie-Q, it was best expressed as wavelength. It was just way easier. And so what do we get out of this? This is called energy density. And so the energy density, I'll write that out. Energy density as a function of wavelength. Remember, this is mostly in the visible. It looked like this. It is almost identical in terms of how it looks to a Maxwell-Boltzmann. It's like kind of eerie. The equations were completely different. But it's just really kind of striking how similar the curves look. I don't think there's really any meaning to that. It just is happenstance. And let's see what we're able to do with this. You recall that. And this is, of course, a function of temperature. It's really the only thing that you can change about a light bulb to affect how the light bulb works. Because there's some engineering, you know. So for the maximum to be around, I think it was around 550 nanometers. Always label your axes. 550 is green, and this is what the sun looks like. And that works when the temperature is around 5,500 K. So to mimic the sun, which is good for us, that's how our eyes are going to work best, is if we have an artificial sun, you need to have a wire at 5,000 K, and that's not many metals can do that. And that was like one of the hard parts about figuring out how to make light bulbs, was finding the right metal that can take that temperature and not evaporate immediately. And these are also in vacuums, right? That doesn't help. Well, it keeps them from burning up. Okay, what else can I say about this? So there was a rise. Now remember that the rise is due to the degeneracy, and it was proportional to 1 over lambda to the 4th. So remember that wavelength is getting shorter. So as it gets shorter, 1 over a smaller number to the 4th power is going to get bigger and bigger and bigger. And again, that was the degeneracy factor. And I told you, it actually is a gigantic effect. And then what brings us down is, of course, the Boltzmann factor. And the Boltzmann factor says, once a photon's energy, hc over lambda, is greater than kT, and again, so T will be like 5,000 K, and it's a pretty big number. But the wavelengths get short enough, the frequencies get high enough that that ratio ends up being greater than 1. Again, the energy of a photon is greater than kBT. Now the Boltzmann equation says, I'm not liking that so much anymore. And that makes sense. I mean, why would a light bulb start spewing out gamma rays or X-rays? That's ridiculous. I mean, turn on a light bulb and, you get fried, right? So I'm kind of lucky it works that way. So the Boltzmann factor kills it, and the two balance out to give us the curve that you see. So anyway, there's that. I haven't right now put any Planck distribution questions. Again, I got 2 more to write, so I'm thinking about a Jacobian and a Planck. Let's see, but again, the utility was a nice segue into quantum. 1 second, I'm going to wipe out the board and we'll keep going. All right, next what we did was we went into into some description of quantum mechanics, and we talked a little bit about how people were noticing some weird things like how light had momentum. That was the photoelectric effect. I think I mentioned some things about heat capacity. I didn't put any of that stuff. That's like minutia. I didn't put any of that on the exam. What I did want you to know something about was the theory of relativity. And it's probably kind of inappropriate for me to mention this stuff in this class, but you can understand, you can see the connection between quantum mechanics and Einstein's theory of relativity. And I wanted to cover that mostly just because I thought it would be cool for you to be able to say that you know stuff about that. And it was useful, right? So remember that Einstein's theory of relativity was not E is equal to 1/2 mv squared. It was far more complicated and has the speed of light in it. And you can also, you know, little party conversation, you can tell people things like, you know, Einstein did not derive E equals mc squared, right? You had to do that on a homework. And I thought that was kind of neat, right? I mean, you get told that as a kid, E equals mc squared, and it's not really true. So, so that's what Einstein derived, and the way that comes about is from the consistency of the speed of light. It's actually, Einstein derived all this from simple geometry. How do two travelers, one person stationary, another person traveling, look at a beam of light and measure the same speed, right? So it ends up being a geometry problem, and from this, that's what energy is. Okay, now photons don't have mass, so that's gone. So for a photon, what Einstein was able to do was derive that a photon has momentum, which, how could it? It doesn't have mass. But again, so everything is starting to look really weird back in 1920s. And so photons have momentum even though they have no mass. You know, anything goes, right? But that explains the photoelectric effect, because how could a photon hit an electron and impart momentum if it does not have momentum itself? It has to convert conservation of energy and momentum. The energy of the electrons change when light blasts it out of a solid material. That's the photoelectric effect. But its momentum changes too. So light has to have momentum and energy. That it has energy is obvious, but anyway. Okay, so there's that. And so of course if we were in physics, this is what we'd be doing. But in this class, all right, remember that's pronounced de Broglie. De Broglie, the derivation is a little bit more complicated. He wrote his thesis on this, but ultimately it's just kind of funny to me is that he just switches the letters. The letters just get switched around. But what he's talking about is not a photon, he's talking about anything, particles made of matter. And of course we mostly talked about electrons. Based on the last lecture, remember that there is at some point, we live in the world we live in where Isaac Newton's equations of motion, F equals ma, all that stuff works just fine. But if you get to the world of the small, then that stops working, and then quantum mechanics, everything has to be solved with quantum mechanics. That generally happens when you're talking about very light masses, and that means electrons and protons to a lesser extent. A particle with mass has a wavelength. And again, that's like back in 1920, this is utter nonsense, but to the best of our ability, it seems to be true. Okay, so de Broglie comes up with this, wins like the youngest Nobel Prize winner in history as a result, and so Schrodinger, I think I mentioned to you, no one knows how Schrodinger derived the Schrodinger equation, because he first worked out the Schrodinger equation. His actually first publication was on the hydrogen atom, so he really went for the, went for the top prize at the very first step, and people were so interested in that result and further interpretations. I think no one ever asked him how he did it, and so a lot of people have had to reverse engineer the result. But the way I tried to do it, and again, this is not how he did it, but so if he's going to have some description of of matter as a wave. Now remember, look at what I'm writing here. This function, 2 pi over lambda times x, that's the formula for any wave. As soon as you've traveled lambda, from 0 to lambda, cosine has gone from 0 to 2 pi. So that works for anything, right? So that's a good starting point. We know it has to be true. And we're going to call that cosine kx. Where k, of course, is the wave vector, 2 pi over lambda. Okay, now, we also know from basic physics that p squared over 2 times the mass is kinetic energy. That ends up being equivalent to 1/2 mv squared. But people don't like to use 1/2 mv squared in physics, and a lot of this came from the physics community, so this is their 1/2 mv squared. And it ends up being kind of convenient. So knowing that, let's see here. So I've got 1 over 2 times the mass. And then what would be momentum? Momentum would be h squared over lambda squared. And that's from right here. Okay, and we've already decided that k, I'm going to put this in terms of k. So I can see that k is 2 pi over lambda. If I want to put k in here, so I'm going to have a k squared, but I have a little bit of a 2 pi problem. So what I'm going to do is I'm going to multiply and divide by 2 pi squared and just absorb that into h. So that's where h bar comes from. H bar squared k squared over 2 times the mass. Okay, so again, wave equation, which is, there's no special quantum derivation here. This is true for everything. This is just a statement of kinetic energy, and the only thing weird is that we've plugged in a little bit of this relativity de Broglie thing going on. Now, what you have to do is figure out how to connect the two, right? How do you get this wave equation to tell you what the energy is? And that was Schrodinger's thing. Now, again, the actual derivation was probably a little bit more complicated by everyone's best guess. But regardless, it's still true that no matter what you can do is, let's just get the constants, right? Constants are constants. So the Schrodinger equation is just going to have some constants. Okay, how do you get k squared out of the cosine? We'll just take the double derivative. Right? Now, double derivative of a wave, cosine, sine, actually any of them, is going to pick up a minus sign, so you just add a minus sign. Now you're already adding constants anyway, just add another one, add a -1. Okay, so this is the first operator, right? That's the kinetic energy. That's kinetic energy, and it gets a little hat. Remember the hat? It gets a little hat for being an operator. And what you do is you put that wave function in front of it. All right, so then what? Then what? Well, it spits out a k squared, so you get h bar squared, k squared, over 2 times the mass. And of course, the wave function also comes back. So notice that this is an eigenvalue equation. Now, if you have wave functions of the Hamiltonian, then your eigenvalue is the energy. Now remember that I also have generic forms of operators. There's more operators than the Hamiltonian. There's momentum, there's position, angular momentum. We did a little bit with that. And you don't necessarily assume that the Hamiltonian wave function is the same as any other operator, which was really where this got a lot more difficult, right? I think it wasn't terrible up to this point, but when we started getting into the fact that we have other operators, and sometimes things that work with Hamiltonian, like sine or cosine, do not work with other operators like momentum, that was really difficult. So remember that my generic eigenfunction, I use wave function for Hamiltonian, I use eigenfunction for other operators. And just to kind of make it clear what I'm talking about, so these are both eigenvalue equations. This is specific for the Hamiltonian, and this is how we generally express it in general. And operator, eigenfunction, eigenvalue, eigenfunction. Now, last bit about this is, remember I mentioned that this is actually the mathematics of stringed instruments. This is the mathematics of music. So the fact that Schrodinger did not come up with eigenvalue equations, they were already well known. And
again, that was how people figured out how to describe stringed instruments. Wind instruments too, right? Waves. Stringed instruments have waves. They're stationary waves. So there you go. It ran into the exact same thing. Okay. So, so this is one of the fundamentals of quantum mechanics, is that everything has to be an eigenvalue. Although when you run into the problem of the wave function for one operator not being the same as the other, recall that instead of eigenvalues, you use expectation values. So I'll get into that in a minute. So I wanted to remind you that I love to do things this way because it's easier, but it doesn't always work. For like when you have a sine wave and you're trying to get the momentum, you've seen that example like a zillion times now. And what you then do is you use the expectation value way. But before I get to that, I'm going to talk a little bit more about that. So this is important. Let me put another check by one of the most important things, which is, of course, that the wave function squared, and I'll use this little d tau. So I may be doing x, y, z, maybe I'm doing r theta phi. Right? Regardless, the Born interpretation of a wave function, back in the day, they're looking at this and they're like, you know, it worked. Schrodinger worked on the hydrogen atom and he got the right energy, and that was like, whoa, you know, Born had done the same. He had that homework problem. Born had done the same thing, but his model had a flaw, which was that a circulating electron ought to be generating light, and that the atom would actually fall apart as a result, and that's like a big flaw. And there's no way that's not true. Schrodinger does not have that problem. But people were looking at the wave function thinking like, well, does that mean anything? Or is it just a means to an end? Is it just a tool that by itself doesn't mean anything, but it has this weird characteristic of delivering energy? Born said that it's a probability density, right? But you have to square it. You have to square it, and then it's a probability density. And we already know you don't need to be deriving quantum mechanical theorems to know that if it's a probability density or distribution, that it integrates to 1. Now, the wave functions are in position. So now the wave function itself can be negative, and it can have a complex stuff in it, right? Oh, here, I'll build something inside of a trap. So it looks like that. Okay, that looks like an n equals 2 particle in a box. So wave function can be negative. They can have the letter I in them. So that's awesome. It really complicates things. Actually, I think I mentioned to you that if you ever derive quantum mechanics without complex, e to the I, you can do it. It's just like 1,000,000 times harder. So it's worth the effort to get used to e to the I, x, and all that jazz. Because if we didn't, it would have actually been worse. Anyway, so all right, so going back to the wave function squared being the probability density or distribution. So now it's inherently positive. So I'm doing this thing over here. Now it's inherently positive. And I can interpret like if I was to ask, what's the probability that the particle is found on the left side of the box? Well, it would be that area, this area right here. And seeing how I've tried my best to draw it even Steven, then that area would be 0.5, right? The entire area, if I integrated the entire area, it's 1. It means that it's somewhere between 0 and L. But if I ask what's the probability it's on the left side, if that would be this area, and that area I'm certain would be exactly 0.5. So Born's interpretation, it's actually really quite sensible. It's just unfortunate sometimes that, these eigenvalues, they could get pretty awful sometimes. Remember when you did energy of the hydrogen atom, or energy, it actually was pretty bad, it was harmonic oscillator. That one was pretty awful too, wasn't it? So these can unfortunately get pretty complicated. Let's see. There were some other things that I don't think I'm going to put in this test, but like you can't have a sharp turn, it can't fly off to infinity, wave functions can't do those things. I have not, I didn't put that on this test. And again, I have some questions to write still, but I don't think I'm going to, just because I just didn't really feel like it really. So, what happens year to year is I get different ideas in my head about what I feel like writing. And there's enough material that a test can be written, with new questions, not too hard. Okay, now I want to go back to what happens when this fails, because that also brings us to the uncertainty principle. Those are actually related. And I haven't emphasized that too much. But what happens when that fails? What happens when, okay, in the language I'm using here, I'll work downward, but then I'll stop. What happens when you have an operator like momentum or kinetic energy operate on a wave function of the Hamiltonian and not get, some number? I guess I'll use my omega symbol. All right, what happens when that happens, right? Weird, unbelievably annoying. Wave functions of Hamiltonian are the real wave functions, right? We think that reflects reality, and that should give us all the answers. Yet the eigenvalue equation can, and to be blunt, frequently fails. So it's like, well, then I guess I don't have all the answers. And actually you do. Recall that what you have to do is we're going to use the expectation value way. So expectation value of this operator, and again, momentum, sine wave, momentum, the example you've seen, literally about 20 times now. That's a good example. And so what ends up happening is you integrate over all values. Now, we're talking about x, y, z, right? So we're talking about just integrating over all space if it's like a free wave. Integrating from 0 to L if it's a particle in a box. Again, it's kind of obvious, isn't it? And so now what's kind of weird, and I've never actually quite understood this, although it's derivable, is you take the complex conjugate of the wave function, the operator, and the wave function. And again, I'm going to use a more generic d tau in case maybe this is just an x, but maybe it's x, y, z, maybe it's r theta phi, and so that's our symbol for that. And now remember we derived how this works, so I guess it kind of makes sense. It is kind of a weird looking thing. It doesn't quite, the thing is, it's that for an operator like x, let's say you're doing average position, then you can actually put the wave function right next to its complex conjugate and do this. And so I'll say that tau is only the x position. If I go from minus infinity to infinity, that certainly would be all values. Okay, so this would be the average x, the expectation value of x. Those are the same thing. Two words for the same thing, right? And what I like about this is that it looks like the Maxwell-Boltzmann. There's the probability distribution times the thing you want the average of, right? You've heard this a zillion times. And so this, I like this. This makes perfect sense. The problem is when you have an operator like momentum, when there's a derivative operating on the wave function, and then you cannot do this. And so, I kind of hate that because I like showing this because it makes a lot of sense, with Maxwell-Boltzmann. By the time we've done Maxwell-Boltzmann and you see this again, you should be like, oh yeah, all right, I've done that enough now, that's not weird. But when it comes to momentum or a bunch of the other operators, then it does get weird. You just have to work with this as it is. So anyway, blah, blah, blah. What did I want to say? Oh, and I want to point out, actually, I don't know if I said this in class, but this actually can make a lot of sense. Like, why does this fail? Tell you what, let's look at, oh God, where am I at? Okay, let's think about vibrational. Okay, so here is V, here is X, where X is the bond length, X of 0 is the equilibrium bond length for like an O2. I talked at length about O2 yesterday. Okay, so let me point out why the eigenvalue equation would fail. So here's our ground state wave function. So if I was to try to get the momentum of the wave function for vibration, it would not work. This is one of the ones that'll fail. But now think about this. Doesn't it make sense that it failed? When you've got this thing on this potential surface, when you're expanding, you come to a point where you're going to start to go backward, right? A turning point. Now, maybe you can go further than that, and let's not wade into the weeds here, but so when a bond is stretching, at some point it's going to come backward. So it's moving, it stops moving, and then it starts moving again. The momentum's changing. It's positive and large because it's stretching. Eventually it turns to 0 because it's going to go back. So now it's increasing in value, but now but it's negative because there's a compression. Okay, again, this is all freshman physics that should make perfect sense, right? But notice that the momentum changes. Right here, the momentum is large because it's expanding or contracting. Out here, it's got to be small, if not 0, because it's got to turn back. So look at the eigenvalue equation. The eigenvalue equation says, what is the momentum? What is the momentum? Well, there is no the momentum, right? Because it changes depending where you're at. So you're giving it this whole function. You're giving it the whole function and asking it for one value of the momentum. There is no one value of the momentum. It depends where you're at. But you didn't feed that information into the momentum. You didn't give it the wave function at a particular value. You gave it the whole wave function. And the whole wave function experiences a range of momentum. So how could it possibly spit out one number? Well, it doesn't. It can't. But that's actually good. And hopefully that makes more sense why you would have to then use an average value. On an average, this case would actually be 0. Because if it wasn't 0, then eventually the bond would stretch and stretch and stretch and forever and forever. Well, that's actually a bond breaking, right? But you can't break a bond with a harmonic potential. That's why we had those Morse potentials and whatnot. Anyway, I'm really getting off nonlinear, right? That's not what we covered next. What we covered next was, free wave. Yeah, this bears some repeating. Kind of. I'm jumping around time. I'm kind of doing it on purpose because, you've seen this stuff before. It doesn't, I think it actually comes across better. Hopefully you understand it a bit better. You don't have to follow, the way we did things in time. So I'm kind of going backward now. So remember that when we started on our quantum, we had no potential energy because that was just easiest, right? We had to figure out all the stuff about operators that I just talked about. And I didn't want to complicate it too much. So we had no potential energy and everything, there was no Y or Z. So this particle, it's a particle that exists in a one-dimensional universe. There's nothing else there, because if there was, there'd be potential energy. If there's another particle, they might hit. Well, what is hitting? Well, it means that there's a potential energy increase when you get too close. Okay, but there is no potential energy in a free wave. Therefore, it's an empty universe. There's only one particle because it doesn't interact with anything, nor are there any walls. If there were walls, it would interact with it. Again, there's no potential energy. So anyway, we did a bunch of stuff with this. Oh, and we also got another reason to introduce this is to get you used to the letter I. Now, the letter I appears so much, especially like in the rotational part of the hydrogen atom. E to the I phi, right? So you were going to see the letter I a whole bunch, and I knew it. So that's why I wanted to get you used to complex functions and whatnot when we did the free wave. And you were also able to interpret things, right? This is moving to the right, and minus ikx is moving to the left. And then one of the more interesting ones is, another like theorem of quantum mechanics, not that I want you to like memorize this, is when you have solutions, so remember these are valid solutions to the Schrodinger equation just has the kinetic energy operator for the free wave. And these are perfectly valid solutions. It turns out that you can make linear combinations of the valid solutions, and those are valid solutions. And so it gives you, it like immediately expands your ability to write solutions to kind of like a sickening degree. Remember, we actually used this. We used this when we had to do the rotational parts of the hydrogen atom because we didn't like traveling waves for px and py. So we made linear combinations of e to the I phi plus or minus e to the minus I phi. Now, another important thing about this is that, okay, so this is correct. The momentum of this is positive, the momentum of that is negative, the momentum of that one is 0. So, one way to say that this wave function is composed of a right and a left traveling wave. I guess there's a 1 over square root of 2. I forgot. I don't really care about that stuff. Normalization, right? The one thing, though, that also bothered me, as a college-educated student, just to remind you, we talked about this, is the mainstream, lamestream fake news media, when they talk about this, and they frequently do, they say that quantum mechanics states that a particle can move to the left and to the right simultaneously. And that's false, right? That's really annoying because it makes this seem ridiculous and harder than it is, and people will then reject it. It would be helpful to describe it correctly to begin with, and then it actually makes more sense. What happens is that when this particle is created in this empty universe, you were not given the knowledge of what direction it was traveling. So without that knowledge, you have to, with no knowledge, you would say, well, it's 50-50 moving right, 50-50 moving left, and you have to write the wave function that way. And guess what? Even though it is moving one way or the other, it truly is. But when you don't know it, and you make measurements on it, this is the right wave function. This will give you the right answer. Even though it's really doing one of these, so this is really nuts, but this has been tested. Even though it is truly moving to the right or truly moving to the left, if you do not know it, and you do experiments, measure momentum, and measure position, and measure, this wave function gives you the right answer, and these don't. If, however, you are told that it's moving to the right or moving to the left, and you use those wave functions, whichever one it is, if it's moving to the right, this one gives you the right answers, position, momentum, all the things you can measure. These will not give you the right answer. Look, go figure. Now, Einstein actually said quantum mechanics is wrong because of what I just said. Einstein said that's nonsense, that there's no way that that's true. Einstein was proven wrong. It is true. Everything I just said about this thing being the right wave function for properties, if you are not told which way the electron is moving, even though it is truly moving either left or right. Again, mind blown, right? But this is why you go to college. You should know this stuff. Okay, that's free wave. All right, let me wipe out the board. Now we're going to do particle in a box, uncertainty principle. Then we're going to talk about potential surfaces. I'll remind you of some of that. And then multidimensional. That will actually finish it because, again, that brings us up to the end of test 2 and test 3 you just had. So I'll be right back. Okay, so what did we do next? All right, after we gotten all those fundamentals down, then we started introducing model problems. And those model problems are introduced by the potential energy. Potential energy tells you whether there's another particle present, tells you if there's a wall present. And we got into kind of this rote mechanism, right? Okay, here's a problem, what's the solution? Here's a problem, what's the solution? Here's a problem, right? On and on and on and on and on again. This class tends to be traditionally taught that way. It's like learn by example after example. Also, every problem is unique. This is the thing I actually don't like the most about quantum, is that every problem is solved differently. It's like in math, when you do a derivative, it's just bring the power down, power to the -1. I mean, I like that because once you know that, everything's real easy. But in quantum, no problem is the same as any other problem, and I hate that. Anyway, I actually try to avoid this class. I'm actually better in thermo. Anyway, but they assigned me to do this, and I agreed, so that's what's going on. So what did we do after the free wave? We did the particle in a box. Right, so of course it's the same as the light bulb, which is why I introduced the light bulb to begin with. And let's see, so remember that the way you do this is, in a flat potential, the wave function is always a right wave and a left wave. Okay, but now that's not enough, right? I mean, I don't know what, I know that K is related to the energy, right? K squared, h bar squared over 2m is the energy. So I know what K is, I know what X is, I know what I is, but I don't know about A or B. And actually, you know what? I don't know K. I don't know what the energy is, come to think of it. So as much as it's like, okay, here's the wave function, you're actually not done, you're not even close to done. For one, you don't know what A and B are, and then you need to know the energy so that then you know K. Once you have that, then you know. But what do you do? Well, in this case, there's boundary conditions, right? So what you have is that the wave function at x equals 0 has to be 0 because the wave function can't leak to the left of the track. If the potential energy is infinity, for the wave function to move to the left would require an infinite amount of energy to beat the potential energy, and it doesn't have that. So the wave function has to be 0 at x equals 0, and then from what we get from that is that the wave function now has to be a sine wave, right? Because only sine is 0 at x equals 0. So now I know it's a sine wave, but now I need to know, and that means that a is equal to minus b. That's how you know that. All right, now I need to have the innards of the function. I need to know sine kx, but what's k? Now it turns out that we have two boundary conditions, right? So we have to start at 0, and we have to end at 0 for the same reason. If we move to the right of L, the wave function has to be 0, it has to be 0 forever. So for the wave function to be 0 at x equals L, what that does is it doesn't affect the function, that's already been decided. It affects the innards of the function. As it travels to the right, it's got to land on 0. And the way to do that is we got to hit pi at some integer once we've traveled L. Of course, we're in the x direction. So there you go. And again, once you've had trigonometry, you can figure this out. Now remember, I also said, because I was complaining before, right? The thing about quantum is we can figure out most of the stuff without using the Schrodinger equation. So I solved the Schrodinger equation without using the Schrodinger equation. And that's annoying, I hate that, but whatever. But you notice I just solved it without having to really do much work, so I guess that's kind of cool too. Now, the next thing is, remember that I said that you now have to, I said it's sort of equal, you now need to normalize it. And that's something you folks kind of struggle with sometimes, or sometimes a little bit of a what's wrong question or a trick question. I'll throw something at you, but it's not normalized, and the answer is wrong, and the answer, well, it has to be normalized. So we normalize things after the fact. Okay, now because you have to have a multiple of pi, what you're also seeing are excited states. So you're seeing quantized energy levels, right? So here's the lowest energy wave. Again, you've seen that a zillion times. But there's the next allowed energy level, that the wave can be 0 on the left and right. Because of that, because you have to be 0 on the left and right, energy cannot be the energy cannot be any value. There's discrete values of the energy, and those energies are, if I write it down, n squared, h squared over 8 mass L squared. Okay. So n, of course, is the quantum number. That was your first introduction to a quantum number. Oh, it can't be 0. It's kind of it can't be 0. There's a 0 point energy to this. There's always energy. It's a whole number. And again, this is just because you have to land on 0. That bothers me a bit. You have to land on 0 at the right and the left. And so you have the wave function. You can then use the eigenvalue to calculate the energy, and there's the energy. And yeah, there you go. And notice, so there was really a lot of value to this because you're seeing ground state versus excited state. I actually did have one of you. I told you, the one thing that annoys me the most about whenever there's a hydrogen atom question is the ground state's 1s, and 2p, 2s, 2p, 3s, 3p, 3d, yada, yada, yada. Those are excited states. If you can take a hydrogen atom and take it out of the 1s state and put it in the 2p state, it's fine. It's just an excited state. One of you said, no, 2p states don't exist. Then why are you even saying 2p, right? If it doesn't exist, why does the concept of it even exist? And so this was our first foray into seeing why things have ground and excited states. And there's an infinite number of excited states, and we know their energies, and they have different properties and different transition moments. You did spectroscopy on a particle in a box. And remember, there's, not only do you get some concept of ground versus excited states, remember that dyes work this way. Remember I showed you that little video on quantum dots, which are a big thing. Those are made with TV screens, and this explains how quantum dots work. You make a bigger one for the red pixels, you make smaller ones for the blue. So already we're getting, some basic concepts of how things work, but it's also useful. So, all right, now this then sets us up for the uncertainty principle, and the uncertainty principle certainly is certainly one of my least favorite things, and I think basically everyone's least favorite thing, and it has to do with the fact that, remember actually I was actually watching the very first lecture. I actually watch the videos sometimes, and I said then that really this class is about probability. Maxwell-Boltzmann probability distributions. The wave function squared is a probability distribution. Well, as soon as we're talking about probabilities, you can have uncertainties, right? Uncertainties, sigma, variance, all that stuff is part of the science of statistics, and statistics has to do with probabilities. So, big surprise here that we run into some statistical manifestations, which was, again, the uncertainty principle, and that was for when you have two operators. Now, this is another thing I started introducing. At this point, I had shown you that there's really a whole bunch of operators. There's an operator for everything that can be measured. I can measure momentum, I can measure energy, I can measure position, I can measure angular momentum. Those are all measurables. Even on electrons, I can do that on a single electron. We've been doing that for like 30 or 40 years now. And there's a quantum mechanical operator that corresponds to that measurement. That's really the whole idea behind operators. But the uncertainty principle says that so remember a variance is, and again, this is actually this is not a quantum thing. Let's do the variance of the first one. It's this. This is a standard. Look in a statistics textbook, and this is the variance, right? So this is a well-known thing. So if you take the sigma, which is the error bars on a graph, it's just the square root of that. So there you go. So there's your sigma. Okay, the uncertainty principle says that the variance in one operator, expectation values, times another operator is greater than, I think I messed this up. We have this commutator, right? Remember the commutator? Get little hats, there we go. And isn't that squared? I think that's squared. My notes don't have it squared, so now I'm freaking out. I don't remember anymore. Yeah, I think it's squared. I'll have to double check that, but sorry. But so again, this is the idea. And what it means is that, well, it's like, so let's default to the one example that everyone likes the most, right? Position and momentum. Remember, there's actually a whole bunch of uncertainty principles. Any two operators that have non-zero commutators have an uncertainty principle. Now, that was a mouthful, but let me remind you what a commutator is. So position and momentum have a non-zero commutator, and remember that this is xp minus px. And using the techniques I showed you in class, that's h bar over I. So you knew how to do that. Actually, remember how you did that? It was like this. Remember how you saw this a zillion times? For when we were talking about whether something was separable or not, have it act on the wave function and divide out the wave function later. That was actually the first time you saw that. And that's how you can figure out the commutator's h bar over I. And what that means is that since this is non-zero, the commutator is non-zero, you can't know where something is and how fast it's going. And yeah, that's, I don't know really what to say about that other than there was all this stuff. There was some, yeah, I guess there's really not much else I can say about it. You know, all these formulas, again, I'm pretty sure that it's squared. Hopefully the formulas are correct. But I don't really get a lot out of this. So this is why I don't really like covering this stuff here, because I look at this and I'm kind of like, all right, so, you know, I see this. Now I can actually prove this. In grad school, I show grad students how to prove this, so, but it would take a while, so I just gave you this. Actually, you know where it comes from? It's from this. It's like dot products. A dot B is equal to the absolute value of A, absolute value of B, cos of the angle in between. So cosine can be at most 1. Anyway, that's where this formula comes from. Okay, the commutator can be evaluated this way. So again, all these formulas, all right, I've done them, but I look at this and I'm like, so what? So that's why I don't like this stuff. However, remember what we talked about. We talked about how you can, I'm going to do some particle in the box. I'm going to manipulate the way they look, which is perfectly fine, by the way. I'm going to put like a Gaussian shape, and I'm going to have the same box, but, and again, there's, I'm not actually drawing eigenfunctions of the particle in a box, but that's actually okay. We can experimentally actually do this. We can actually create wave functions that are not the same as the eigenfunctions of the particle in the box. And sorry, it's a grad school thing. It's actually surprisingly easy to do this. And so what the uncertainty principle, as much as I was just making fun of it and saying it's terrible, it explains why this is low energy, low kinetic energy, and this is high energy, right? And the reason is that you have less certainty in position. It's somewhere in this box, but you're not sure where. So with less certainty in position, you have more certainty in momentum, and that means that it's not traveling as fast. If something is not moving at all, or barely moving, you have some fair certainty in its speed. It's not very big. Now this guy, you have a lot of certainty in its position. It's basically right in the middle. It's for certain, right in the middle. But that means you have very low certainty of its momentum. Now, if something has low certainty in momentum, how can it be going slowly? If something's going slowly, you're not given a lot of wiggle room, right? If it's moving quickly, then you get yourself a wider range. If something's going 1, 2, or 3 miles an hour, that's a spread of 3. If something is going on average 100 miles an hour, it could be going plus or minus 50, right? So, as a result, the higher uncertainty in momentum means it has more momentum. If it has more momentum, it has a higher energy, right? Because momentum is energy. Now remember, I also composed this into waves, and this one plus this one, and then the same here, except that there's more waves. And I also told you about how momentum waves are what you would measure if you measured momentum. And so if this one is composed of only a few momentum waves, your momentum measurement will always give like one of, either that value or that value. But for this one, with like 20 or 30 momentum waves, you would keep measuring a different result as you measure momentum, so you have less certainty. So actually all this stuff makes sense. I hope it makes sense, I just don't quite see it when I do it this way. So actually I don't think I have any questions on the test like this. It annoys me. So anyway, but I hope that this does help you understand that whole, high school you heard you can't know where something is and how fast it's going. And that's true. And this gives you, a college level understanding of what that really means. Actually kind of winding down, I see I have about half an hour left. Once we did this, we actually kind of went backward a bit. We got to more simple potential surfaces where, okay, well, you know why this is a little bit of a step up, literally a step up, is that the potential surface is now changing, right? So, whereas, it's either infinity or not, here it's a finite step. Now, it turns out that the fact that the potential is flat means that the wave functions are still e to the ikx plus e to the minus ikx. That's still true. It's always true when the potential is flat, even if there's a step. But what happens is the wave functions, you don't, a plus b here, you don't necessarily have the same coefficients, and you don't have the same k's. Now, remember the k's are related to energy. So this would be, God, I'm writing really small, aren't I? I didn't even realize it. So, I, k, 1, x. Okay, now, On the left side of this step potential, you're going to have a lot of momentum because you don't have any potential energy to whittle away your energy. And on the right, you're going to have less K, less momentum, because some of your energy was taken up into potential. Now remember, we also have to be smooth and continuous. And from that, you can figure out your A's and B's and C's and D's. And you can do things like, say, if the wave starts out to the right with low energy and is moving to the left, then if it penetrates the barrier, it will never reflect, which means you can do things like wipe that out. Now that's specific to the problem. If I stipulate that this is a particle that was coming from the right to the left, then that's valid. But if I didn't stipulate that, you'd have to keep that term. Oh, anyway, blah, blah, blah. Now what do we do with this? We were able to define reflection and transmission, and it half made sense. So what do we get? Reflection, so percent reflection, which ended up being, what is the absolute value of B? B is the reflected wave, A is the oncoming wave, and the way that looked on a graph of energy, energy divided by the potential energy, is that the reflection is 100%, right, 100%, until you have enough energy to cross the barrier. Now that's perfectly sensible. So here, the quantum mechanics does, I hate to use these highfalutin words, it's very normal, it's classical, because if it doesn't have enough energy to cross the barrier, it doesn't. But what's really funky is that the reflection does not go immediately to zero if you do have enough energy. Now that's weird. So this is like half quantum funkiness, half it's actually kind of normal. The transmission, of course, is nothing gets through until you have enough energy over the barrier. But then, it's a reflection of literally a reflection of the reflection. The transmission goes up, but it's not like straight up, right? So again, that's where it gets weird. So you have enough oomph to throw a ball over a wall, and you can see that your ball is going to crest the wall, but it comes back and hits you anyway, right? It's kind of like from some kind of kids movie or something. And so that's, again, a little bit of an introduction to quantum. It's a little dynamical, right? I even showed you some of those videos. And so now you're seeing a little bit of the weird behavior of quantum, and that got even more weird when we talked about the finite barrier. And the finite barrier, we didn't solve that. Remember, I have a handout that does that. In case you felt like looking at it, it is 5 or 6 pages of algebra. It's not too hard, So instead of a step, we allowed the step to de-step at some point, and you've got region 1, region 2, region 3, so you have to have smooth and continuous, figure out the A's and B's and C's and D's. Now, so imagine, right, that's why there's 5 pages of algebra in that little handout, and once I have all that, then I can figure out the energies and whatnot. I can figure out the transmissions and the reflections and whatnot. 5 pages of algebra, not too surprising. And it looks something like this. So a little wave, and then it hits the barrier, it tunnels through. Same waviness, but less amplitude. And so what that's saying is that even though this wave has less energy than the potential, if the width of the barrier is kind of short, it actually can get through it anyway. Now again, this is a prisoner in a supermax. This person should not be able to get out ever, but suddenly just literally like an X-Man just appears outside, specifically Nightcrawler. But anyway, so this is like utterly bizarre. And I also I think I pointed out that this is called tunneling, and we do see this behavior like with water. With the H atoms, the protons in water are moving around in ways that they shouldn't be able to. It can affect protein conformation. So what is really unfortunate is that people who try to model this on the computer they need to try to incorporate this effect into their models, and it's really freaking hard. The computers like have steam coming out of their ears because it's a really simple model, just Isaac Newton, F equals ma with atoms, because that's okay for the most part. But when it comes to the tunneling behavior, that's pure quantum mechanical, so they have to try to find ways to incorporate that in their models, and it's a real biz knocker. Now, in this case, you see, I'm going to do percent transmission. When you do this one, you also see more complex behavior. I'm going to do, again, the x-axis is E over V. In that one, you see definitely some strange behavior on this one. So there's one. What you see is there's actually an initial rise, and then you see these resonances, and they kind of look like this. Okay. Now, again, what's weird is that there's some probability of going through the barrier, that's tunneling, if your energy is below the potential, like before V1. So if your energy is below the potential, you still might get through it. The probability is low, but it's not zero. And then what's kind of cool is you see these resonances. At certain energies, you go through the barrier as though the barrier doesn't exist. And even though you pick up energy and you think that that would continue, actually no. If you have too much energy, you actually are less likely to get through the barrier. But then it kind of comes back, and then it goes away, and it comes back. And again, this is just nonsense. But we can measure this. We see this behavior, this resonant behavior. We see this all the time. And really sophisticated experiments like with X-rays, and sometimes with even lower level stuff, you know, like water, right? You don't get more simple than water. So again, a little bit of quantum weirdness, things that, you know, behavior, you know, part of the purpose of this class is to show you things that maybe you observe experimentally, but never could explain, never could understand without all this quantum, this and that. Okay, next bit is multidimensional and then rotation, and that will finish this up. Let me clean out the board. Okay, so what was next after that? So I guess I am doing this in order. It was multidimensional. And really at this point we're just in a run up to the hydrogen atom. And as I don't know if I think I mentioned this just once, but I didn't emphasize it. One of the reasons we stopped this class on the hydrogen atom is that, oh no, I did say this, because you can't solve it anymore. Any other problem beyond the hydrogen atom, you can't solve it. For all the reasons I just mentioned, due to the separability problems. So that's why we actually stopped this class there. And if you want to learn more, of course, you go to grad school, like I mentioned before. So when we got to multidimensional, there's two things about this. One of them is that it's just a run up to the hydrogen atom, and that's like the stopping point. So that makes sense. The other is degeneracies. That degeneracies exist. 2px, 2py, 2pz, 3dz squared, 3x squared, y squared, yeah, blah, blah, blah. So you see that behavior for the first time with multi-dimensional. And so like a particle in a 2D trap, and the wave functions are, look kind of cooler, right? They look like this. And hopefully, some of my computer stuff was, I hope it made this class a little bit more interesting. It's kind of terrible, but anyway. So we have from 0 to Lx, and from 0 to Ly and the y direction, and the wave function ends up, I forgot the normalization, so I won't put that, so I'm just going to do x and y. Recall that this is where you started learning about separability. If the Hamiltonian can be written down to sub-Hamiltonian, so if we can take the Hamiltonian and break it down into like one for x and one for y, and you do that, you prove that via the thing that hopefully you've come to learn and somewhat fear is that little expression. It's just a little useful expression for a zillion things, right? So you do that, and you see if you can break down the Hamiltonian into parts, where each part has its own variable. In the case of like a two-dimensional particle in a box, there's Hamiltonian terms with only x, plus or minus, whatever. Hamiltonian terms with only y. What happens is that the wave function is a function with just x times a function with just y. And recall that, sometimes I look at that and I'm like, well, that's true of anything. And no, it's not. Sine x sine y, that's cool. Sine x plus y, or sine x plus y. No, that does not work. So separability also gives you a framework to solve this. And if you can't do this, then I don't know that it is solvable. Except maybe you could use a computer to do it. And everything, instead of sines and cosines and e to the ikx, it's just a giant table of numbers. Again, that's like the stuff you start learning in grad school. Because that's what you have to do when you get past the hydrogen atom. Okay, so what happens here? I forgot the normalization, so I'm just going to say this is sort of right. It's sine nx pi x over lx sine. So now we picked up a new quantum number. And if Lx and Ly are equal, then you can have degeneracies because, what was the formula? It's, n squared, so nx squared plus ny squared, h squared over 8m. Again, if the lengths are the same, this only works if the lengths are the same. You see that you have the possibility of a degeneracy, because if you're in excited state in x, but in the ground state in y, you could be in the excited state in y and the ground state in x, and those would have the same energy. So, I mean, that's kind of like duh, right? But degeneracies end up being really important, right? They're important in the hydrogen atom. Remember some of the last lecture where we talked about rotational degeneracies, 2L plus 1, well, that's actually the same thing. But anyway, this ends up being like really important, and again, especially if you go further with this, it's a thing. But so, and I didn't even spend a full lecture on this. There really wasn't. I mean, there really was not much to say other than separability, writing the wave functions as functions, and literally how many different ways could you say that, right? So we didn't say too much about this. What we then did is we went to the 2D rigid rotor, and we're getting into rotational quantum mechanics, which rotational quantum mechanics is pretty rough. And although it wasn't too bad for the 2D rigid rotor, when we got to the 3D rigid rotor, then, we're also getting into those problems of, like, it's so complicated, we're not even going to try to solve the Hamiltonian. We're going to go look in the old textbooks and like, okay, here's the answer. So again, we did that a bunch of times. And of course, this was also, we were definitely in a run up to the hydrogen atom, because remember that the 2D rigid rotor wave functions, e to the I phi, that's actually in the hydrogen atom. So that was, it was maybe interesting to learn about rotation and quantum mechanics, but really we're trying to get to the hydrogen atom. So recall that what we have is a post and a string, and on the string is an object, and maybe it's a cat. It's a cat's head, and it's going round and round and round, and defined by an angle phi. So phi is the angle in the xy plane, and theta, of course, when we get to 3 dimensions, is the z guy. So for the 2D rigid rotor, we've still got kinetic energy. Is still, you kind of miss this, don't you? Double derivative of x, double derivative of y. Those were the good old days, right? Now I showed you a little bit about how you really can't work this problem. I mean, you could in x and y, but that would be awful, even though it starts out looking kind of easy. Really, you want to put it in r, theta, and phi. Well, sorry, cylindrical coordinates. So we're going to fix r. So you're going to really want this in phi. And it turns out that it's kind of some hideous algebra. I didn't make you do it. I've made other classes do it. It turns out that double derivative of x, double derivative of y ends up just being double derivative of phi. Again, the angle of the xy ends up being the double derivative of phi. So, I mean, unbelievably easy. Now, there's no potential energy, and so that's the Hamiltonian. That's the Hamiltonian operator. It's just the double derivative of a coordinate. So it is no different than a free wave. And so therefore, the wave functions are e to the I m phi, where m is a new quantum number that comes about from boundary conditions, and we've talked at length about that. So m being a boundary condition thing can only be an integer. It can be plus if you're rotating clockwise, minus if you're rotating anti-clockwise. And remember, I talked a little bit about how there's similarities with the particle in a box, and I spoke at length about that. I'm not going to bring that up again. What else I want to say? Let's see. I can tell you that the energy of the rigid rotor is, of course, angular momentum. Now, since this is a cylindrical coordinate thing, 2D rigid rotor, the angular momentum is only in the z direction. Remember, that's the axle of the wheel. So angular momentum squared over 2I is the energy. I is, of course, the moment of inertia. And based on, then do the wave function, what you find that is m squared h bar squared over 2I. Looks just like a free wave, right? But instead of k squared, you have m squared. I mean, it's like ridiculous. One difference is, of course, that k, the free wave momentum, can be 0, 1, 0.2, 0.3, blah, blah, blah. It can be -2. That's a particle moving to the left. Whereas m has to be a whole number. And the difference arises is because if we draw the track, the wave going about the thing has to, God, I drew that awfully, but the wave has to bite its tail. And that is a stipulation, it's a boundary condition that requires m to be a whole number. So that's where it's different than a free wave. Oops, camera died on me, batteries. So sorry about that. I'm hoping that the thing showed you that we got up to this point. Actually, I can add there's a little light on it. It tells me when the battery is running out. So I think we got to the end of the 2D rigid rotor. And again, there really wasn't too much about this. It really wasn't anything terribly difficult. Although, the derivation from double derivative of x, double derivative of y to the angle, that actually is kind of hideous, which brings me to my next point, which of course is now we go to the 3D rigid rotor. And when we introduce theta into the mix, okay, so minus h bar squared over 2 times mass, double derivative of x plus double derivative of y plus double derivative of z. Now turn that to r theta phi. And I've never even tried this myself. I don't have a handout on it. I'm sure the algebra would be mind-blowing. But it's, someone's done it, it's doable, it's been known for a long time. But it's hideous, no doubt. Of course, what does the Hamiltonian look like? So we still have the 3D rigid rotor. So of course we've still got minus h bar squared over. Now of course I can't use m for mass anymore because that's a quantum number. R squared. Of course R is fixed for the 3D rigid rotor. It's not for a hydrogen atom. So that introduces some complication there. But for the 3D rigid rotor, remember mass times r squared is the moment of inertia. Okay, that simplified things a bit. And then what is all this multiplied by? 1 over, oh my God, sine theta. And remember that this is when separability, this whole separability thing really gets nutty. Not only is this Hamiltonian just ridiculous in its own right, but you run into a really nutty problem with separability. Okay. Of course, we're going to see if the wave function is separable into theta and phi parts. And we hope that that's, of course, equal to the energy times theta, phi and theta wave functions. So this is the idea. And so, yeah, I mean, look at this. It's actually, you know, I'm kind of still used to the hydrogen atom, so this doesn't even really look that bad. But the real problem that you run into is that one, because we have a theta and a phi in the same expression. So that introduced a complication, and the solution was to multiply the whole thing by sine theta squared, and that was fine and good. What you ended up doing is you were able to show separability, but a weird thing happened, which was that the energy ends up picking up a sine theta squared, and that made it belong to theta. So let me write that down, and let me also divide out the wave functions. So, you know, this is also where these expressions, they really just mushroom, right? They just get gigantic, and there's not much I can do about it. Let's see, what happens when I'm doing the separability thing? So I have wave functions on the right, and I'm dividing them out on the left. Of course, I do the same thing on this side. So this ends up being energy, but I've multiplied by sine theta squared. So what you end up with is, okay, here's the division of the wave function on the left. And we see that the phi has a standalone mini Schrodinger equation, so that was nice. Having multiplied by sine theta squared, you end up with sine theta on top. And here's the phi wave function hiding underneath. Here's all the sine d phi, sine phi d, theta, d theta, sine theta, yada yada yada. What do we get? We get the wave function. 2I being mr, mass times r squared, energy over h bar squared. So I've done some factoring, and here's that sine theta. Okay, so yeah, I know, really a mouthful. But again, the important thing was that you have a mini Schrodinger equation with just phi in it, and then you've got a mini, although not small, with theta, a little Schrodinger equation with theta. And so again, we covered separability, and hopefully it wasn't really mind-blowing. You just kind of could assume that it worked that way. But what really got nutty here was that now you were seeing like a hierarchy of the mini Schrodinger equations. So remember that each one is solved on its own, and by solved I mean what are the wave functions, and the final wave function is just you multiply the individual solutions. So this one ends up being, that's the 2D rigid rotor, so we assume that it's still the 2D rigid rotor wave function, and so this ends up being, remember that this is minus its quantum number squared. And again, two m's, I got an m for the quantum number and m for the mass, that sucks. Anyway, so the rest of this has to be equal to plus m squared. And so that's kind of weird. And also that the energy is part of this one. So the energy funnels down into, you know, like you have secondary Schrodinger equations, you have primary Schrodinger equations, because the energy, the thing you really care about the most, is funneled down into one of them. And, you know, there's nothing really special about that, it's just different. And we know that all this is equal to m squared. And again, the thing I've harped on a zillion times, it was literally solved in 1783, something like that, because this ended up being a big thing in engineering. You see this stuff all the time. And of course, the wave functions were the spherical harmonics. And yeah, I don't know, there's really too much more I want to say about it. With the wave functions, of course, we can then calculate the energies. And energy of the wave function, of course, that would mean theta phi. And we can express that as like a total angular momentum over 2I wave function. And that is h bar squared over 2I, L times L plus 1. So it's starting to look, we're getting some really big divergences here from what we've seen before. Everything with all the energies were always h bar squared, k squared over 2m, 2 mass, h bar squared, m squared over 2i. I mean, they always look the same. And instead of h bar squared, L squared, it's L squared plus L. So it's not terribly different, but not exactly the same as what it looked like before. Remember that because there's actually there's two angles, a theta and a phi, that you have two quantum numbers, right? That's another thing that multidimensional does. It gives us more than one quantum number. We have the L quantum number, which is like the primary one, and then you have like a subordinate, the M, the 2D rigid one, which again, you look in that 18th century math textbook, and there's stipulations on if L is this, then M can be that. And that was just like when finding solutions, that was something that happened. So so depending on what L is, M can be minus L plus 1, dot, 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 0, dot, 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 plus L. And so if L is 0, that is not rotating. And so M has to be 0. So that's non-degenerate. Remember, so we're also seeing degeneracies. If L is 1, you got a p state. And so you could have minus 1, 0, plus 1. So that's px, that's where we're going to get our px and py and pz. Sorry, this time the camera ran out of memory. Okay, sorry, back to task. All right, so another thing about the rotational energy here is that if L is 0, which is an S state, then there's no rotational energy, and therefore an S state represents a particle not rotating. Kind of like, all right, L is 0 means you're not rotating, and for the 2D rigid rotor, an M of 0 is you're not rotating. So unlike the particle in a box or the harmonic oscillator where the particle, where things are always moving, you can choose not to rotate. Now the reason I bring that up is, because actually I brought it up several times, but as we move into the hydrogen atom, and you know that the 3D rigid rotor are the hydrogen atom's angle parts, the S state does not rotate. Now several of you on test 3, a majority of you, still answered questions saying like, oh, well when the 1S state is rotating near the nucleus, automatically no points because it's not rotating. Now I don't know what it's doing, but actually, I mean, that's like a good question. Is the hydrogen atom just like bouncing back and forth like on a paddle ball or something? I don't know, but it is not, despite its round structure, it is literally not doing this. And we talked about that several times. The only way you know that something has some kind of kinetic energy, and rotational kinetic energy, is a node. And that means P states, D states, those have nodes. But this, perfectly round, there are no nodes. So anyway, I got miffed at that because I warned you several times to look out for that, and I engineered those questions just in case you answered that way. So, okay, so that was the 3D rigid rotor. Now we get into the hydrogen atom, and I'm not going to say too much. Let me just bring up a little bit about the wave functions, and then we're going to stop there because I'm out of time. And as I said, we're also in test 3. So if you feel like you need a review for test 3, then I'm just going to leave up the test 3 review session. And that way you've had technically like 4 full hours of review. You have the lecture Wednesday, which is still today, for me anyway. It's so weird. Time is so weird for this class, the way I film sometimes 2 weeks ahead of time. So you have that lecture, which is a legit review. This, which is 2 hours, then you can watch the 3rd lecture. And I know that's like a lot, but then again, that should just basically do you for the exam, right? So that's cool. Let me do the board. We're going to just talk briefly about the hydrogen atom. Okay, I'm just going to, the hydrogen atom was test 3, but let me just kind of summarize a little bit about how the 3D rigid rotor fits in with that. And also, remember that where we have one of the bigger changes between the 3D rigid rotor and the hydrogen atom. One was just the Coulomb operator, and I asked a question on the final, 3rd exam about the Coulomb operator. Why is the hydrogen energies, why are they negative? Everything else was positive. Why was the hydrogen atom energies negative? The answer was the Coulomb operator. So what you do is you basically get the 3D rigid rotor and you just tack on the Coulomb operator. You got a hydrogen atom. And remember, R is not fixed. Now because of that, it was really just a bunch of algebra, but it was kind of hideous how you had to do the separability. You separated the angle parts, and then you have the radial part, the radial miniature Schrodinger equation, and the energy funneled into the radial part. That means that the radial is like the most important part. Okay, so what does that look like? Minus h bar squared over 2 times the mass. And remember how I'm always so pissed about how I can't use m for mass because of the 2D rigid rotor quantum number. It's like, I don't know people, when they were developing this stuff, they realized how annoying that would be. It drives me nuts. Okay, now remember that we manipulate the radial operator, the radial kinetic part of the operator. Remember, I think it was on a homework, or maybe I did it in class, where it can be expressed equivalently 3 different ways. And the product rule is how that always happens, right? So the product rule is, if you think about it, think about when you calculated the energy of the harmonic oscillator, when you calculated the energy of the 1s electronic state of hydrogen. The product rule was what made everything work. The product rule was how we were able to manipulate the radial part of the kinetic energy, and you did so such that you had double derivative of r times the wave function. Okay, so what you end up doing is, it's kind of clever. You end up simplifying it. Not that it looks simple, but you could simplify the radial, primary Schrodinger equation for hydrogen. It was in its most simple form as long as you had r times the wave function. So anyway, that's why you see it that way. It was just an algebra thing. I don't know that there's any special meaning. Okay, then you get the rotational kinetic energy. And what you do here is you assume that, here I've got L times L plus 1. So of course that's the rotational energy part. And that means that you are going to solve this. You have to solve, every time you want to know what's the wave function, what's the energy, you have to decide on an L first. So you have to make L 0. Okay, then you get this differential equation, which is awful, but we do know how to solve these, or a computer knows how to solve them. And then you get the energy. Okay, great. Now make L1 and redo the whole thing. It's tedious, but really once you get to L of 2 is a D state, L of 3 is an F state. Once you've done that, you've got the periodic table solved, so it's not that big a deal, right? So, and then we see our R times the wave function. And I know that those can cancel, but we actually tend to leave it this way because we always like to see R times the wave function. And okay, then we've got, where am I at? Then we've got the Coulomb part for pi E naught. Remember I was telling you, you had that homework about atomic units, and there's no H, the mass is 1, 4 pi E naught is 1. It's really clever. I can't believe anyone ever thought of that. That was neat. Okay, we have R times the wave function again, and that is equal to E R times the wave function. So now don't worry about this. I won't have this on the test. I just want to point out some cleverness here. Is that when you solve all this mess, your solution, you just fold this together, and then whatever is the solution to this differential equation mess, you divide that by R, and that's the wave function. So the solution to this is R times the wave function. So you divide that by R, and you get the wave function. I know it's a little bit like, what? But anyway, it's just a clever math trick, and I thought it was very clever that they did this. Now, we have this set up. You can recognize, okay, here's like a linear kinetic energy of the thing just moving. This is rotational kinetic energy. Of course, if it's an S state, then this term is 0. Remember, that's how you did one of the problems on when you did the eigenvalue equation. You made L 0 because it's way easier. Coulomb Of course, it's an eigenvalue equation, so E times the wave function. There was this one attempt to simplify this thing, because again, it's the differential equation is like ridiculous. So you recall there was a lecture, actually 2 lectures, where I said, oh, what if R was close to 0? And then we could make it smaller, the differential equation like way smaller. And what we found is that the wave function would be like R to the L. And if R goes to infinity, that one was actually a little bit tougher. You found the wave function was like e to the minus R over A naught. And there you go. And yeah, so like I say, that's where we got into the beginning of the 3rd exam. And spectroscopy, that 1 week and a half of talking about the electromagnetic spectrum, and then we had kinetics, and I do have kinetics on the final exam because I think those are relatively easy questions. So I know it was like really packed in at the end, but those are, of all the mathematics, the kinetics part are the easiest. So I do have a kinetic question on the final, and I have a enzyme question on the final. And I'll go ahead and tell you what I have on the kinetic question. Let me just go ahead and tell you. If you ever do anything with this stuff, okay, so you're like a hospital administrator, right? Look, not many of you are actually going to become doctors. Some of you will, right? Some of you have already gotten in. But, a realistic thing is, maybe if med school doesn't work out, try public health. That's a growth industry, and it has pretty good pay, and you're still helping people. So I would really recommend that. A lot of folks, to be blunt, that didn't get into med school, who asked for letters of recommendation, that sure enough, a year later, they're asking for public health. Again, it's a really good career. Maybe then one day you're a hospital administrator. Now that would happen if you're also a doctor. I bet that kinetics would be very useful. Patients in, patients out, right? It's reversible. You had the question on the last exam about disease states. Sick person, well person equals to sick people. So this stuff you might actually use it. Now remember that the way that on that last homework set, once you could set up the differential equation, you just use a computer to solve it. But remember that what it did was, and so this is what I have on the final. The little Wolfram website, I tell you what I inputted and I tell you what its output is. It tells you like e to the minus bt plus, it has some unknown factor times like c or something, right? And then what you have to do is figure out what that unknown factor is. So again, I'm putting that's one of the derivational questions. The reason I'm doing it is that this stuff actually might be directly useful to you at some point. Computers can solve it, but when it comes to like solving diffie-Qs, there's always an unknown factor. It's from a boundary condition. The computer doesn't know what you're talking about. It doesn't know the boundary conditions. So it's also, even if you really just don't know what's going on, you can actually still figure this out just from pure mathematics, which are kind of lower level. Now recall that what you do in this case is you would either say, if time goes to infinity, you would probably get all products, or if time is, not goes to, but is equal to 0, then you would have all starting material. Now between one or the other, that would give you your boundary condition. So if time is infinity, then that's e to the minus infinity, so that's gone. If time is 0, that will be 1. And again, over here, you would either have all products or all reactants, and then you can solve for your unknown. So anyway, I threw that on there. I just wanted to let you know that was a little bit of an unusual question for this class, but I thought it would be like one of the easiest ones to solve, so I put that on there. And yeah, that's really about it. I don't really have any other hints. And so I will see you all, remember, Wednesday, 1 o'clock. So I'm posting this. This should be Wednesday night. I'm going to try to process this and get it all done. And you have plenty of time. I will send the cheat sheet. I have not finished the exam yet, so I haven't sent the cheat sheet yet, but I'll do that as fast as I can. Send complaints to the head office. No one's in the head's office. All right. Okay, all right, I'll see you all on Wednesday.